Welcome. Today's lecture is about gamma ray universe. A new window to the universe opened up a few years ago, and we are able to study gamma rays from celestial sources with considerable confidence. Although gamma rays from celestial sources were recorded almost 30-40 years ago, there were always 1 sigma or 2 sigma results. And you must have a minimum of 3 sigma results, preferably 5 sigma results, before you can be absolutely sure about the detection. And that change occurred in 1991 when NASA launched a giant gamma ray telescope, which was named the Compton Gamma Ray Observatory. It functioned for 9 years, and then it was brought down. It had several instruments that you can see over here, which operated in the energy range 20 kilo electron volt to 30 GeV. More recently, in the year 2008, a giant gamma ray telescope named the Fermi Gamma Ray Large Area Telescope was launched. It operates in the energy range 20 MeV to 2 TeV. 1 TeV is 10 to the power 12 eV. So it's an enormous energy range. Now this unparalleled observatory has revolutionized gamma ray astronomy. As I said, till the Compton Gamma Ray Observatory was launched, most of the detections were 1 sigma or 2 sigma results. You really need 5 sigma results before you can be absolutely sure of the detection. Today, with the Fermi Gamma Ray Telescope, we are talking about 11 sigma results. So gamma ray astronomy has come of age and is now the latest window to the universe. Now this is the gamma ray universe. This map, taken based upon 5 years of continuous data with the Fermi Large Area Telescope, is the entire sky, the entire universe in gamma rays at energy greater than 1 GeV. Now let's look at this a little more carefully. Now, the emission, gamma ray emission from the sky can be decomposed into 2 parts. One, there is diffuse emission, and then there are point sources. In this slide, you clearly see diffuse emission, and then you see thousands and thousands of point sources. Let us see the point sources a little more clearly in this slide. What you see here are active galactic nuclei, blazars, supernova remnants, then supernova pulsars, globular clusters, high-mass X-ray binaries, galaxies, starburst galaxies, diffuse emission from galaxies, and what have you. So this is a catalog of the Fermi Large Area Telescope, a catalog of point sources. Now let us dig into what are these gamma ray sources. They are either young pulsars, as I said, very old millisecond pulsars, supernova remnants, the interstellar medium of our galaxy and external galaxies, active galactic nuclei, quasars, and of course gamma ray bursts. And more recently, gamma ray bursts from 2 neutron stars spiraling in, emitting gravitational radiation, and then coalescing, producing gamma rays. We talked about this in one of the earlier lectures. Now, what are the emission mechanisms that produce gamma rays? Well, there is our good old synchrotron radiation, where relativistic electrons are gyrating in a magnetic field. we saw that the Crab Nebula emits gamma rays via synchrotron radiation. We also saw that the Crab Pulsar emits pulsed gamma rays, which is also synchrotron radiation. Then you have relativistic Bremsstrahlung, relativistic electrons colliding with ions, Coulomb collisions. Then there is a very important mechanism which we shall now discuss, which is the decay of neutral pi meson. And finally, there is inverse Compton scattering. There's nothing inverse about it, but it's really Compton scattering, and we shall spend a good fraction of this lecture discussing Compton scattering, which is the photon scattering of relativistic electrons. All right, now let's look at the gamma ray emission from our galaxy, the Milky Way galaxy. There are two components to gamma ray emission from our galaxy. One, there is a soft spectrum. That means the energy range in this picture is lower energy gamma rays. And then there is the hard spectrum, which looks very different. If you compare the two, it looks very different. Most noticeably, there is this dipole-like structure at the center of the galaxy. Now let's look at gamma ray emission from the interstellar medium, and that's what is interstellar medium of our galaxy, the Milky Way galaxy. And that's what is shown over here. Now, it's the same thing that is shown over there. We shall soon discuss the mechanism, the radiation mechanism that is responsible for gamma ray emission from the interstellar medium. As we shall see, it has to do with the interaction of cosmic ray particles, protons in particular, with molecular gas in the interstellar medium. If you remember, the molecular gas is a rather thin layer about the plane of the galaxy, only about 60 parsecs. Of course, the neutral hydrogen layer is very thick, but the molecular gas and associated dust is a fairly thin layer around the plane of the galaxy. And that can be seen very prominently through the infrared emission emanating from the dust as well as diatomic molecules. Now, let us discuss the emission mechanism from the interstellar medium. Well, relativistic protons, these relativistic protons probably come from extragalactic energetic sources, from nearby pulsars or what have you. They collide with atomic nuclei in the interstellar medium, in the molecular clouds, and they produce pi mesons. Now, pi mesons come in three varieties. They are either pi plus, pi minus, or neutral pi mesons, which is the pi zero mesons. Now, charged pi mesons, pi plus or pi minus, decay to mu mesons, which are lighter than the pi mesons, and neutrinos. And the mu mesons in turn decay to electrons or positrons, and that is shown over there. Pi plus, for example, decays to mu plus and a muon neutrino. Pi minus decays to mu minus and a muon antineutrino. And then the muon decays to a positron plus an electron neutrino. And of course, you have a muon antineutrino. We are not discussing neutrinos at all in this lecture. I just want to say that the mu mesons produced in the decay of pi mesons, charged pi mesons, eventually decay to positrons and electrons. And they may produce some radiation, which we are not tracking in this particular lecture. Now let's concentrate on the pi zero meson, the neutral pi zero meson. Now it is well known that a neutral pi zero meson decays to 2 gamma rays. And the energy spectrum of the gamma rays produced in this reaction is rather broad, and peaks around 70 million electron volts. So when you look at the interstellar medium and it is glowing in gamma rays, it is really glowing at an energy of around 70 MeV. And what is really happening is that the pi-zero mesons, which are produced by the collision of relativistic protons with the nuclei in molecular clouds, decay to gamma rays. Now that's the interstellar medium over there. And that's the diffuse emission due to pi-zero decay. But supernova remnants, which we discussed in the previous lecture, which of course are well known through the synchrotron radio emission, which you see over there. This is Cassiopeia A, which we discuss in several contexts. But these supernova remnants also emit gamma rays. And that magenta color over there is gamma rays from Cassiopeia A detected by the Fermi Large Area Telescope. Now here is another supernova remnant. This is the false color image. The lighter colors are more intense regions. It's a gamma ray emission of some supernova remnant. And the gamma ray emission is again due to the interaction of cosmic rays with the molecular gas with which the supernova remnant is interacting, ramming into, possibly a molecular cloud. Now let's discuss supernova remnants. As I said, the Fermi telescope has detected gamma rays from more than 30 supernova remnants in our galaxy. In the relatively young supernova remnants, like the Crab Nebula, for example, the spectrum is very hard. In other words, you have gamma rays up to high energy. And this can be attributed to synchrotron radiation by electrons accelerated by a neutron star. We know that the Crab Nebula emits gamma rays from near the light cylinder. But that's not what I'm talking about now. These charged particles are finally deposited into the Crab Nebula, and there they radiate by gyrating in the magnetic field of the Crab Nebula through synchrotron radiation. Of course, you need very high energy particles and very strong magnetic fields before the synchrotron radiation can be observed at as high an energy as gamma rays. That's only possible in very young supernova remnants like the Crab Nebula. In older supernova remnants, the electrons do not have that high an energy, and the magnetic field strength is also decayed due to adiabatic losses as the supernova remnant expands. And therefore, you do not get any synchrotron gamma ray emission from older supernova remnants. But you do get gamma ray emission from older supernova remnants, but they are softer in the spectrum. In other words, the energy of the gamma rays is much lower. And careful examination tells us that this emission is due to protons, cosmic ray protons, interacting with the molecular gas into which the supernova remnant is ramming into in the interstellar medium. So it's really not gamma ray emission from the supernova remnant itself, but it is a gamma ray emission from the periphery of the supernova remnant, where you have a compression of the magnetic field of the molecular cloud because it's being rammed by a supernova blast wave, and then the protons are gyrating in that magnetic field. Of course, young pulsars like the Crab pulsar are powerful sources of gamma rays. Here is, of course, the Crab Nebula seen in the entire electromagnetic spectrum, at radio wavelength, at infrared, visible wavelength, ultraviolet, X-rays, soft X-rays and hard X-rays, and of course low energy and ultra high energy gamma rays. This is the Crab Nebula. But the Crab Pulsar is also a source of pulsed gamma ray emission. Now, the emission from pulsars is clearly synchrotron radiation. And this radiation emanates not from near the surface of the neutron star, but far away near the light cylinder. Let me remind you in a minute about the light cylinder in case you've forgotten. Now, gamma rays are produced near the surface of the neutron star by relativistic electrons that are accelerating along curved magnetic field lines. But these gamma rays are absorbed by the magnetic field themselves, and they produce electron-positron pairs, which finally radiate at radio wavelengths. So the gamma rays produced very near the surface of the neutron star don't really get out because the magnetic field has a very large optical depth for the photons. Fermi Large Area Telescope has detected gamma rays not only from the Crab pulsar, which is an old story, but from several young pulsars, nearly a dozen or so young pulsars. Now let me remind you once again about the light cylinder. Here are the magnetic field lines of an inclined neutron star. This is the rotation axis of the neutron star. The light cylinder is what is shown in red, and the radius of the light cylinder is such that if a particle were co-rotating with the central neutron star at that radius, it would be going at the speed of light. In other words, the circular or tangential velocity v, which is equal to r omega, that v will be equal to c, the speed of light. Therefore, if I solve this equation, I'll get the radius at which the velocity becomes equal to c. Therefore, the radius of the light cylinder is c over omega. So faster the pulsar spins, larger is omega, closer is the light cylinder. As the neutron star slows down and its period lengthens and omega increases, the light cylinder radius will increase proportionately. Now, why am I bringing in this light cylinder now? This is just to remind you of what we discussed in our lecture on pulsars. Here is the central neutron star. There are gamma rays produced very close to the neutron star surface. Near the star, the magnetic field is very strong. The charges are not allowed to cross the field lines because the Lorentz force is very, very strong. They can only slide along the curved field lines. And since the field lines are curving, these electrons will radiate. They will radiate into a narrow cone, and the width of the cone will be the angle, opening angle of the cone will be 1 over gamma, but gamma is the Lorentz factor, 1 over square root of 1 minus b squared by c squared. And therefore, the radiation is essentially emitted in a tangential direction to the magnetic field. Now, this is how the radiation from the pulsars are produced. These gamma rays decay into electron-positron pairs, and they in turn they are of much lower energy. Therefore, the synchrotron photons produced by the electron-positron pairs is not in the gamma ray region of the spectrum, but they are the radio wavelength. But now let us look at what happens to these charges, electrons, as they go near the light cylinder, whose radius is c over omega. Near the light cylinder, the magnetic field is much weaker than near the surface of the star. The magnetic field of the neutron star is roughly a dipole magnetic field, and the strength of the dipole magnetic field decreases as 1 over r cubed, where r is the distance from the center of the star. Therefore, by the time you go to the light cylinder, the magnetic field is not 10 to the power 12 Gauss. It is significantly weaker, and therefore electrons can now defy the magnetic field, gyrate around the magnetic field, and produce synchrotron radiation from near the light cylinder. This is how the optical radiation, the X-ray radiation, and the gamma rays are produced from pulsars like the Crab pulsar or the Vela pulsar. But please remember this, as the pulsar ages, its period will lengthen. This is the plot of the magnetic field versus the period of rotation. So pulsars are born spinning fast, like the Crab pulsar or the Vela pulsar, but as they get older, their periods lengthen, their omega increases, their omega decreases, the period lengthens, and therefore the radius of the light cylinder, which is C over omega, increases. And therefore the magnetic field, which decreases as 1 over r cube, decreases. Therefore, in older pulsars, the magnetic field near the light cylinder is too weak for any significant synchrotron radiation. If you remember, the energy radiated per unit time by a relativistic electron in synchrotron radiation is proportional to B squared gamma squared, where B is the strength of the magnetic field and gamma is the Lorentz factor. Therefore, as the pulsar ages and the dynamo becomes weaker, gamma ray emission will cease and you will just get radio emission, which is of course coming from very close to the surface of the star. Therefore, we can expect gamma ray emission only from very young pulsars, like the Crab pulsar, which is 1,000-year-old, or the Vela pulsar, which is just 10,000 years old. Now let us remind ourselves about the dust and molecular gas around the plane of the galaxy, seen so clearly through their infrared emission. Now let us look at the gamma ray, diffuse gamma ray emission from the interstellar medium. And this is the picture we saw before, and I'm showing it again for a particular reason. You notice that if gamma rays are produced by protons interacting with the nuclei of dense gas, then you would expect the gamma ray emission to mimic the infrared emission. But the gamma ray emission from our galaxy is rather wide in its latitudinal distribution. You see gamma rays from very high north galactic latitudes. You see gamma rays from very high south galactic latitudes. So there is a puzzle. What is this high latitude gamma ray emission, which seems to be very diffuse in the top magenta box or the bottom magenta box? What is this diffuse high latitude galactic gamma ray emission due to? In 1928, when these gamma ray observations were first beginning to come, early gamma ray satellites, there was emission already detected at high latitude. And yet no one had any viable explanation, as I just told you, way back in 1988. Besides the interstellar medium, you need dense interstellar medium for protons to interact. That medium isn't there at high latitude because the molecular gas is only 60 parsecs in thickness, half thickness. The only other source of gamma rays are pulsars. But Crab and Vela pulsars, of course, are well-known gamma ray sources. So could the high latitude gamma ray emission be really due to young pulsars, which we are not resolving? The answer is no, because one expects gamma ray emission, as I said, only from young pulsars, because you need the light cylinder to be close to the neutron star so that the magnetic field strength hasn't decreased very dramatically at the light cylinder. But young pulsars will be found near their birthplaces. Pulsars are born due to the collapse of massive stars. Where are the massive stars to be found? In the plane of the galaxy, where the molecular gas is. Therefore, young pulsars, like the Crab and Vela, you would expect them to be very close to the plane of the galaxy. Therefore, the high latitude galactic emission cannot be due to young pulsars like the Crab and Vela pulsar. You will say, but look, you told me in the previous lecture that pulsars have very large space velocities. So pulsar may be born near the plane of the galaxy. but they could migrate to very large distances, and therefore they could emit gamma rays even though they are at very high latitude. But that won't work, because yes, it's true that pulsars can migrate, but as they migrate, they age, and as they age, their periods lengthen, the dynamo weakens, and therefore you would not expect any synchrotron radiation from older pulsars. Therefore, neither the interstellar molecular gas interacting with cosmic ray protons nor young pulsar could be invoked to explain the high latitude gamma ray emission. So this was the puzzle in 1988 when the first NASA gamma ray telescopes were launched and the galactic emission was first detected. In 1988, a long time ago now, I made a prediction. I advanced the hypothesis that the high latitude gamma ray emission must be due to a large population of millisecond pulsars. Now, millisecond pulsar was first discovered in 1982, and by 1988, only 3 millisecond pulsars were known. But I was invoking a very large, with 3 millisecond pulsars, you get only 3-point source emission. So if you want to explain diffuse high latitude emission, you need thousands and thousands of millisecond pulsars. There are only 3 millisecond pulsars known. But then I stuck my neck out and said, look, there must be a very large population of millisecond pulsars as yet detected. So I stuck my neck out, and the title of my talk was Millisecond Pulsars, a New Population of Gamma Ray Sources. This was at a conference in Finland in June 1988. What made me make such an atrocious and audacious statement? The idea was simply the following. Yes, you're seeing diffuse gamma ray emission at high latitudes, but this is appearing to you to be diffuse simply because the gamma ray telescopes of that time did not have sufficient angular resolution to detect individual point sources. So if your glasses get fogged because you're wearing a COVID mask, then everything looks very diffuse. But then if you clean the glasses with a piece of cloth and wear it and remove your mask, you see individual sources. So that was my crazy idea. So the idea was that this diffuse emission seen by the NASA telescope will someday be resolved into individual point sources, and you will then discover these are in fact thousands and thousands of millisecond pulsars. Now, when I said this, of course, there was a great deal of skepticism in the audience because at the time only 3 millisecond pulsars were known, and I was invoking tens of thousands of millisecond pulsars. Now, why was I doing that? That's because 2 years earlier, in 1986, Dipankar Bhattacharya and I wrote a paper in which we predicted that there will be a very large population of millisecond pulsars with the rotation period between 6 and 10 milliseconds, an extremely low magnetic field of the order of 5 times 10 to the power 8 Gauss. Now, this is the plot that you might be familiar with, logarithm of the magnetic field of pulsars in the y-axis and the logarithm of the period of rotation in the x-axis. Most of the 1,000 or 2,000 pulsars are in this part of the diagram. They have magnetic fields between 10 to the power 12 and 10 to the power 13 Gauss. They are in this region. So what we predicted is a very large population of millisecond pulsars in this oval, red oval, and those dots are the predicted millisecond pulsars which will be detected someday. Now, why won't millisecond pulsars age? Why will millisecond pulsars be at very large galactic latitude? Now, if you remember our discussion of millisecond pulsars several lectures ago, let me repeat it. These millisecond pulsars come from low mass X-ray binaries. The progenitors of millisecond pulsars are low mass X-ray binaries, and they are spun up. Low mass X-ray binaries have very large scale height. Therefore, you would expect millisecond pulsars to have very large scale height. Now, because the millisecond pulsars have extremely low magnetic fields, and these magnetic fields do not decay, they will function forever. Why do pulsars die? Pulsars die because their periods lengthen and the dynamo becomes weaker. The period lengthening P dot is inversely proportional to 1 over B squared. Sorry, P dot is B squared. The period derivative is proportional to B squared divided by the period. Therefore, larger the period, smaller is P dot. And smaller the period, larger is P dot. This is true for normal pulsar. But in the case of millisecond pulsars, the magnetic field is not 10 to the power 13 Gauss, it's 10 to the power 8 Gauss. 5 orders of magnitude smaller. Their period derivatives, P dot, is not 10 to the power minus 14 seconds per second, it is 10 to the power minus 21 seconds per second. In other words, a millisecond pulsar, in the entire history of the universe, its period will only lengthen by 1 millisecond. Therefore, millisecond pulsars will never age. They are youthful forever. Secondly, millisecond pulsars, because they are spinning very fast, the light cylinder will be close by, because remember the radius of the light cylinder is C over omega. Omega is very large for millisecond pulsar because the period is very short. Therefore, light cylinder will be closer. Therefore, they will emit gamma rays, although their magnetic field is only 10 to the power 8 Gauss. 1 over R cube hasn't decayed the magnetic field very much because the light cylinder is very, very close to the pulsar. Therefore, in our paper of 1986, Dipankar Bhattacharya and I had asserted that millisecond pulsars will live forever. Their lifetime will be the lifetime of the universe itself, because their period derivatives are almost vanishingly small, and they will have very large scale heights. So that was the basis of my prediction made in 1988, and the prediction was that the diffuse gamma ray emission at high latitude, which couldn't be explained either in terms of young pulsars or in terms of molecular gas interacting with cosmic ray protons, must be due to a very large population of millisecond pulsars which are emitting gamma rays. There were only 3 millisecond pulsars known at that time. That was a prediction made way back in 1988. So the prediction was there must be a large population of millisecond pulsars numbering tens of thousands, if not hundreds of thousands, and they will emit gamma rays, and they will be located in this part of the log B, log P period. Many years later, in 2009, 21 years after this prediction was made, the Fermi Gamma Ray Telescope was launched. And the first thing that the Fermi Large Area Telescope detected was gamma rays from millisecond pulsars. And the discovery paper that appeared in the cover of prestigious journal Science, the title of that paper was precisely the title of my paper way back in 1988, Millisecond Pulsars, a New Population of Gamma Ray Sources. And what Fermi Large Area Telescope has detected is nearly 150 millisecond pulsars in precisely the location that we had predicted way back in 1986. So the millisecond pulsars are indeed account for the galactic part of the diffuse high latitude gamma ray emission. Now, those aren't the only high latitude sources. There are other sources which are not millisecond pulsars. In fact, they are the majority. They are the active galactic nuclei. Active galactic nuclei of any description, Seyfert galaxies, blazars, quasars, or what have you, constitute the largest population of gamma ray sources. More than 1,500 AGNs have already been catalogued based on observations by the Fermi Large Area Telescope. Now, the spectrum is very hard. Remember, the Fermi Large Area Telescope can observe up to 2 TeV, 2 times 10 to the power 12 electron volts. Now, this gamma ray emission cannot be leptonic in origin. Leptons are light particles like electrons, so it cannot be thermal Bremsstrahlung. It cannot be hadronic either, heavy particle. Hadrons are heavy particles like the pi mesons. Pi 0, remember, decays to 2 gamma rays. But their energy peaks at 70 MeV. Here we are talking of hundreds of GeV, if not 1,000 GeV. So it cannot be either leptonic in origin or hadronic in origin. The only other mechanism that is left is inverse Compton scattering. So let us now discuss inverse Compton scattering. Of course, there are also gamma ray bursts, and there are more than 1,000 gamma ray bursts that have been detected so far. Their origin is not entirely clear. We know that some of them could be coalescence of 2 neutron stars because we have detected them. Some of them could be supernovae of a very special type because we have identified some gamma ray, but there may be other sources of gamma ray bursts also. Then there is this source we saw right at the galactic center. In this picture, we are looking straight towards the center of the galaxy, and the dark band over there is the dust in our galaxy. That is the plane of the galaxy. And then you see this dipole structure. It's like the radiation pattern of an electron, non-relativistic electron in the dipole approximation, except this is enormously large in size. This is 50,000 light years from there to there, 50,000 light years from there to there. Just to remind you, the distance from the sun to the center of the galaxy is only 30,000 light years. So these are 2 enormous structures. And what you're seeing there is gamma ray emission from near the center of the galaxy. These are now termed as the Fermi Bubbles. Fermi because they were detected by the Fermi Large Area Telescope. They extend to 50 degrees above and below the plane of the galaxy. And the spectrum is very hard. The spectrum index is 1.9. Intensity versus frequency, the slope is 1.9. The spectrum of the northern part of the bubble and the southern part of the bubble are identical. So whatever is the mechanism producing these bubbles, they are identical. It's located at a distance of 10,000 parsecs or 30,000 light years. And if the emission is due to electrons, which is suspect, then the energy content of the electrons must be as large as 10 to the power 52x, which is enormous, 10 to the power 52x. The most likely mechanism is inverse Compton scattering. Electrons must have an energy in excess of 10 to the power 12 electron volts. But these electrons, by the time they travel 50,000 light years above and below, will cool because the energy is lost in radiation. And therefore, just like in radio galaxies, we had the 2 lobes at a distance of million parsecs, millions of light years. The electrons would have lost energy, so they had to be in situ acceleration. Similarly here, to irradiate this bubble, the electrons must not only be produced by the central source, presumably the central black hole. Black hole is the center of a galaxy, but these electrons must be accelerated continually. We don't know what this mechanism is. Anyway, let's leave the speculations for a moment. And so in the remaining time, let us discuss Thompson scattering. Now, if you remember, in 1928, Thompson discovered an important effect, for which in 1928 he was awarded the Nobel Prize for Physics. Let us first remind ourselves of Thompson scattering, first discussed by the great J.J. Thomson, who discovered the electron in the Cavendish laboratory. We discuss Thompson scattering when we discuss the sun and the stars. An electron scatters off a photon. Electron collides with a photon, and what you have coming out is an electron and a photon. What really happens is that if you have an electron which is more or less stationary, the oscillating electric field of the incoming radiation will make the electron oscillate at the same frequency. An oscillating electron will radiate at the same frequency, and that's what Thompson scattering is. We discussed this at great length. Now, in Thompson scattering, we assume that the energy of the photon remains unchanged. Namely, the incident energy of the photon gamma I is the same as the final energy gamma F. Now, when a photon scatters off an electron, the electron is bound to recoil. And that recoil energy must surely come at the expense of the energy of the photon. Therefore, the photon scattering can be rigorously elastic, or the photon will not lose any energy at all in the scattering, only if in the rest frame of the electron, the photon has a very low energy. But as I've said many, many times, low or high energy in physics has no meaning. You have to compare it with something. How much energy does a stationary electron have? mc squared, where m is the rest mass of the electron. So as long as the energy of the photon h bar omega is much less than the rest mass energy of the electron will not recoil much when the photon bounces off the electron. So that is the regime of Thompson scattering. The incident photon must have an energy which is very small compared to the rest mass energy of the electron. In this case, we are talking about stationary electron, more or less stationary electron, because what Compton did was to scatter X-rays of electrons in metals. Electrons in metals are moving at relatively low velocities. They are not relativistic electrons. Now, the differential cross-section for Thompson scattering, let us skip all the mathematics. We have discussed this several times before. The Thompson scattering cross-section is 8 pi by 3, square of the classical electron radius. The classical electron radius is E squared over mc squared. All right? The value of the Thompson scattering cross-section is 6.65 into 10 to the power minus 29 meters squared. Cross-section as a dimension of an area. This leads to a mean free path in the sun of half a centimeter. We discussed this at great length. Now let us discuss Compton scattering. It is the same scattering. There is an incident electron and an incident photon, and there is a final photon trajectory and a final electron trajectory. Pi is the initial momentum of the photon, Pf is the final momentum of the photon, Qi is the initial momentum of the electron, Qf is the final momentum of the photon. And this is the scattering we are discussing. Now, the geometric representation of the scattering is shown on the right. This is the incident electron, this is the incident photon, and the angle between the incident photon and the incident electron is alpha I. The photon is scattered, goes in that direction. The angle of scattering between the initial direction of the photon and the final direction is theta. And the electron goes in that direction, and this angle is alpha f. So theta is the angle by which the incident photon is scattered. Now the difference between Thompson scattering and Compton scattering is, we will now be discussing the case where the electron is relativistic. Now EI is the initial energy of the electron, EF is the final energy of the photon, gamma I is the initial energy of the photon, gamma I is 1 over square root of 1 minus Vi squared divided by C squared. Vi is the incident velocity. So it's a very simple problem. You have on the left-hand side of the reaction, you have a momentum of the electron, a momentum of the photon, energy of the electron, energy of the photon. On the right-hand side, you have the photon and the electron. Both energy and momentum have to be satisfied simultaneously. Therefore, to calculate the final energy of the photon, we have to conserve the energy, EI, the sum of the energy of the photon and the electron must be equal to the final energy of the electron and the photon, and similarly for the momentum. Now, this is a very simple, straightforward, high school calculation. You should be able to do it in about 5 minutes' time. I shall not take the time to do this algebra for you. I suggest you do it yourself. It's an extremely elementary calculation of adding up the momentum on the left-hand side, right-hand side, adding up the energy on left-hand side and right-hand side, and equating the two. When you do that, please take it from me. This is what you get. EF divided by EI, where EF is the final energy of the photon and EI is the initial energy of the photon, is given by this formula. I showed you what these various angles are in the previous diagram, so we will not bother about that. Now we are talking about a relativistic electron. How to make this calculation simple? A trick that we have done before. Let us jump onto the relativistic electron. In that frame, the electron is at rest. Beta, which is V over C, is 0. Gamma, which is 1 over square root of 1 minus V squared by C squared, is 1, because the electron is stationary. So in that case, in this formula, in that frame of reference, I put beta I equal to 0 and gamma is equal to 1. The formula reduces to a very simple formula which you would have studied in your BSc physics as the Compton scattering formula in the rest frame of the electron. So the final energy of the photon divided by the initial energy of the photon is given by this expression over there. Now cos theta has a value always equal to or less than 1. And this is a positive number. Therefore, it's always 1 plus some positive number. Therefore, denominator is greater than the numerator. Therefore, what this tells you is that the numerator on the left-hand side is clearly less than the denominator on the left-hand side. In other words, the photon has lost some energy. Where did that energy go? In the recoil of the electron. When the electron gets a kick, it has a certain kinetic energy, half mv squared, and that has come at the expense of the photon energy. This is Compton scattering. This is simple Compton scattering. Now, let's look at the formula again. Now we want to discuss the case of relativistic electrons. When we are talking of relativistic electrons, beta, which is V over C, is approaching 1. And gamma, which is 1 over square root of 1 minus V squared by C squared, is a very large number. It can be 100,000 or even a million. But let us assume that the incident photon, whatever it might be, has an energy less than the rest mass energy of the electron. What is the rest mass energy of the electron? mc squared. But where m is not the rest mass energy, it is m0 divided by square root of 1 minus v squared by c squared. Einstein taught us that in 1905. Or in other words, the energy of the rest mass energy of a relativistic electron is gamma mc squared, where m is now the rest mass. It is mc squared, but m is now not the rest mass energy that you find in Clark's table, but it is really gamma m. Gamma is 1 over square root of 1 minus v squared by c squared. So we are going to assume that this condition is still satisfied. Now, in this case, we will see that this formula will predict that the photon can gain an enormous amount of energy. In other words, the final energy of the photon can be thousands or million times more than the initial energy of the photon. It comes from the same formula from which we derived the Compton's formula by jumping on to an electron going to its stationary frame. But this is the formula in the laboratory frame, not in the electron rest frame. Now, what we will find, and I will make this argument possible in the next couple of minutes, is that typically when a relativistic electron collides with a photon, the photon will gain energy by a factor of the order of gamma squared, where gamma is 1 over square root of 1 minus v squared by c squared. Therefore, gamma squared is 1 over 1 minus v squared by c squared, which can be an enormous number. It can be a million or a billion. So, let's convince ourselves that you will in fact gain an enormous amount of energy. The scattering we are talking about is the following. An electron is moving, let us say, along the x-axis with a relativistic speed, and a photon is approaching it at an angle theta. This is the diagram of the collision in the laboratory frame, which I have named as S. Now let's do a simple trick. We want to calculate the change in the energy of this photon when it scatters off this relativistic electron. Now, this calculation can be done. We have the full formula, which I've shown you 3 times already, but I'm trying to do a poor man's estimate of how much energy will be gained. Now, in order to make a poor man's estimate, let us do a trick. Let us jump on to this relativistic electron and go to this frame S prime. So in that frame, I have jumped onto the electron, therefore the electron is at rest with respect to me, because I am co-riding with the electron. Now in that frame S prime, the photon is coming, not at this angle theta, but at angle theta prime. The angle may be the same or may not be the same. You have to see for Lorentz transformation. Now the important thing to appreciate is that you notice that this incoming photon, I have not labeled it with the frequency nu, I have called it as nu prime. Why? That is because if I am in the rest frame of the electron, and the photon is approaching me, I will see the frequency of the photon Doppler shifted towards the bluer part of the spectrum. In other words, the photon frequency will be blue shifted. Remember, if the photon is moving away, it will be red shifted. If the photon is moving towards you, its frequency will appear to be blue shifted, or the frequency will increase. And that is, of course, given by a formula which I derived for you in our lecture on special relativity. When I am sitting on the electron, the frequency of this photon, which is h nu in the laboratory frame, will appear to me to be h nu prime, and the two are related by Doppler's formula, gamma times 1 plus v cos theta. Now, if the electron is moving very slowly, velocity is very small compared to the speed of light, gamma is 1, and I have only 1 plus v cos theta, which is our good old Doppler shift formula. This is also the Doppler shift formula, but it is that special relativistic Doppler shift formula which I derived for you and used also. So, in the frame in which the electron is at rest, the relativistic electron is at rest, that is the frequency of the approaching photon. Now, the approaching photon will be scattered. It will be scattered to a new direction, scattered by an angle psi prime in the frame S prime. So, photon is scattered by that angle. Will its frequency change? Well, its frequency will not change as long as this frequency h nu prime given by this formula, as long as it is still less than gamma mc squared, where gamma is the Lorentz factor of the electron in the laboratory frame. As long as h nu prime is much less than gamma mc squared, I can regard this scattering in the frame S prime as Thompson scattering, in which the frequency of the photon is not changed at all. So this photon in this frame has a frequency nu prime, and this photon in this frame has again frequency nu prime. So what I'm interested is the frequency in this frame, laboratory frame S prime. So I jump off the electron onto the laboratory. And what I will get is another factor of Doppler shift, namely I had h nu prime, h cancels out, nu prime, which is nu I into gamma 1 plus beta cos theta, which is just this formula there. And then again I'll have a gamma into 1 plus beta cos of this angle, which is theta prime plus psi prime. So it's elastic scattering. So all I have done is now calculated by some simple trick, a poor man's derivation of the frequency of the scattered photon in the laboratory frame. If you didn't want to do this, if you are uncomfortable doing this, go to the original formula and convince yourself the result is there. I'm just trying to make it plausible for you. So now you'll see that the final frequency of the photon will be approximately gamma squared times the initial frequency, provided these angles are all suitable. So there is a gamma here and there is a gamma over there. So please convince yourself that in the most favorable situation, which is head-on collision between the electron and the photon, the frequency of the photon will be increased by a factor gamma squared. So in the laboratory frame, where a photon scatters off a relativistic electron whose energy is gamma mc squared, the frequency of the final photon, the scattered photon, will be gamma squared times the frequency of the initial photon. This is the energy gain in Compton scattering. Now, this inverse Compton scattering is extremely important in many astrophysical consequences. For example, cosmic rays, which I've talked about many times, are produced by quasars and active galactic nuclei, which are billions and billions of light years away. So are the cosmic rays that we observe on Earth coming from a quasar or active galactic nuclei, which is a billion light years away? I don't think so. Why? Because in between, it's not vacuum. The space between the quasar and the sun is filled with cosmic microwave background radiation. It is filled with photons whose energy peaks in the microwave region. These relativistic electrons scatter off the photons, so they will lose energy to the photons. Active galactic nuclei have lots of relativistic electrons as well as lots of photons generated by synchrotron radiation. So I'm trying to tell you about situations where you have the coexistence of relativistic electrons and a radiation field. Therefore, the relativistic electron can interact with the radiation field, and the frequency of the photon will be increased by a factor gamma squared. Now the question is, how will the spectrum of radiation be modified by Compton interaction between the electrons and the photon? let us discuss this. So let us say that there is some region, it could be the intergalactic region, it could be in the vicinity of an active galactic nuclei or a quasar. There is radiation field. What is this radiation? Synchrotron radiation produced by relativistic electrons or cosmic microwave background radiation. So there is an energy density U radiation, and there is a single relativistic electron. Now let us consider a relativistic electron interacting with the radiation field. So far we have discussed the interaction of a relativistic electron with a single photon. Now if I'm sitting on top of the electron, I will find not just a single photon hitting me, I will find photons hitting me from all directions with all possible initial energy of the photon. So all I have to do is for each scattering, I calculate what is the scattered frequency and what is the scattered intensity, and then I integrate over all solid angle over the radiation field. Then I get the answer that I want. I hope it's clear to you what I'm talking about. So let me repeat it. So far we talked about sitting on top of an electron and asking what will be the consequence of a photon scattering off the electron or in the laboratory frame. Now, this electron in this picture is being bombarded by photons from all directions, photons with all sorts of energies. So we have to do this calculation properly and calculate the total scattered power. It's very easy to do this calculation. I will not do it for you. There are two steps to this calculation. Go to the frame in which the electron is at rest and calculate the flux of photons. Flux means the number of photons crossing a unit area per unit time coming and hitting the electron. And step 2, calculate the scattered power. And then jump from the electron rest frame to the frame of the radiation field or the laboratory frame. If you do this calculation, which you will find in all standard books, this is what you will get. The energy radiated per unit time due to Compton scattering is 4 by 3 Thompson scattering cross-section sigma t, the speed of light, into energy density of the radiation field multiplied by beta squared gamma squared, where beta is V by C and gamma is of course the usual Lorentz factor. This is what you get. Now some of you who have carefully studied my lecture on radiation from synchrotron radiation from relativistic electron gyrating in a magnetic field will remember this formula. The energy radiated per unit time due to synchrotron radiation is given by 4 by 3 sigma t c multiplied by b squared beta squared gamma squared, where b squared is the square of the strength of the magnetic field. Remember, b squared, beta squared, gamma squared. Since we were talking of relativistic electron, beta is 1, so I would have essentially written capital B squared multiplied by gamma squared. Now, capital B squared divided by 8 pi is just the energy density in the magnetic field. So what I've done is to cleverly write the formula for power radiated in Compton scattering and the power radiated in synchrotron radiation to look the same. The only difference between these two formulas is in the top formula, which is Compton scattering, you have the energy density of radiation field, which is interacting with the relativistic electron, and the energy density of the magnetic field with which the relativistic electrons are interacting. The two formulas look the same. There they are, same formula over there. Now in both cases, the electron is scattered by the electric field. Now, in the case of the synchrotron radiation, you will say, well, there is no electric field, it is magnetic field. But there is an electric field, which is V cross B. Okay, because we wrote the Lorentz force as E over C, V cross B, so the electric field is V cross B. In the case of Compton scattering, which is scattering of a radiation field with electrons, the electric field is a coherent superposition of the electric field of the incident waves. Remember, the incident wave, according to Maxwell's electrodynamics, can be described in terms of an electric field and a magnetic field. You remember the Poynting flux is E cross H, and the energy is proportional to E squared or B squared. Therefore, in both cases, we are dealing with an electric field. Now let's go back to inverse Compton scattering. It is easy to show that the photon will gain maximum energy in a head-on collision. So if h bar omega naught is the energy of the incident photon, in a head-on collision of a relativistic electron, the scattered photon will have an energy h bar omega max, which is 4 gamma squared into h bar omega naught. This is the maximum, the most favorable configuration for energy loss. Now, photon and electron can scatter at various angles. Now, if you do the average, you pick up a 4 by 3 times gamma squared h bar omega naught. I leave this algebra to you. If you're brave enough, you can do this calculation. Now, the general result, this is important, listen to this carefully. The general result that the frequency of the scattered photon is gamma squared times the frequency of the initial photon is of profound importance in high energy astrophysics, because you know a variety of astronomical sources have electrons with Lorentz factor ranging from 10 to 1,000 or even larger. And we are talking of gamma squared. So we are talking about a million, a boosting of energy of the photon by a million or more. Therefore, your low energy photons will be scattered to very high energy. So here is an example. Let us consider an electron with a gamma of 1,000. It's a fairly modest relativistic electron. Now, if you're dealing with scattering of radio waves in a radio galaxy, the frequency is about 10 to the 9 hertz. It will be scattered to 10 to the 15 hertz, which is ultraviolet. So radio photons will be scattered to ultraviolet energies. A far infrared photon will be scattered to X-ray energy. An optical or a visible wavelength photon will be scattered to gamma ray energy. So this is how you produce gamma rays. You produce gamma rays not by the original process, but all I need is photons which have energy in the visible wavelength, a few electron volts, and if I have relativistic electrons, gamma squared times that energy is in the gamma ray region. Thus, inverse Compton scattering is a means of creating very high energy photons. By the same token, the electrons are also losing energy. So inverse Compton scattering is also a mechanism whereby electrons lose energy because they're giving their energy to the photons. Now, this can have very important consequences. For example, I already said cosmic rays presumably originate in powerful sources like black holes and so on, far away. Now, but those cosmic ray electrons will have to travel through cosmic microwave background radiation. The energy density of a radiation field is A T to the power 4, where A is Stefan's constant. T is the temperature. Now we are talking of a temperature of 3 degrees Kelvin. Now the energy density of the cosmic microwave background radiation, which fills the universe, about which we will discuss in our lectures on cosmology, has this energy density. Therefore, the lifetime of the electron, the same old thing. Like we discussed the lifetime of the stars. We discussed lifetime in synchrotron radiation. It is the energy of the electron divided by the rate at which the electron is losing energy. In this case, the electron is losing energy in Compton scattering, and that is the formula over there. And the lifetime of the electron, or the time over which the electron is lose a significant amount of its kinetic energy, is given by this formula 10 to the power 12 years by gamma. Now, an electron with an energy of 100 GeV will have a gamma of 10 to the power 5. Why? Energy of the electron is 500,000 electron volt. Half times 10 to the power 6 electron volt. All right? That is gamma mc squared. Therefore, if I have an electron with an energy of 100 GeV, that corresponds to a gamma of 10 to the power 5. So if I put in 10 to the power 5 in the denominator there, I will get a lifetime of 10 to the 7 years. So our cosmic rays cannot come from a quasar which is at a distance of 1 billion light years away. Because even light takes billion years to reach us. And the electron needs only 10 million years before it loses all its energy. So the Compton interaction between relativistic electron and the background radiation that fills our universe has very important consequences for the origin of cosmic rays that we detect here on Earth. Now, please permit me a few moments. I want to discuss something terribly interesting and exciting. That is the concept of synchro-Compton radiation. So what I have is some source, an active galactic nuclei, quasar, what have you, where there are electrons and a magnetic field. These electrons will gyrate in the magnetic field and produce low energy photons, maybe radio radiation, maybe infrared or visible radiation, by synchrotron radiation. So I now have not only relativistic electrons and magnetic field, but I also have photons. Now these relativistic electrons will scatter off the photons which were created by synchrotron radiation, and these electrons will be now scattered to ultra high energies by inverse Compton scattering. So I have synchrotron radiation, and those photons have been upgraded to very high energy by Compton scattering. Now, when the same electrons are involved in both synchrotron radiation as well as Compton scattering, it is referred to as synchro-Compton radiation. So what I have is some active galactic nuclei where there are relativistic electrons which have produced low frequency photons by synchrotron radiation. It is the same radiation interacting with the same relativistic electrons, boosting its energy to ultra high energies by Compton scattering. So that is synchro-Compton radiation. The combination, it is Compton radiation riding on the back of synchrotron radiation, if I might put it that way. Now you can have a catastrophic situation. What do I mean by that? Let eta be the ratio of the energy loss rate of an electron by inverse Compton scattering divided by the rate of energy loss rate by synchrotron radiation. Remember, an electron in an active galactic nuclei loses energy both when it emits synchrotron radiation, because that energy of the photon has to come at the expense of the energy of the electron. It is also losing energy by inverse Compton scattering. The two formulae I have shown you a little earlier. And let us say this is the eta is the ratio of this energy loss rates. Now, a catastrophe will occur if eta exceeds 1. Because what happens is when eta is greater than 1, what it means is that the energy lost by the electron through Compton scattering is more than the energy lost by the electron in synchrotron radiation. So, following very interesting thing will happen. The electron produces synchrotron radiation, and that synchrotron radiation is immediately boosted to gamma ray energy. So the intensity of synchrotron radiation doesn't increase beyond a certain point. And what you will find is that finally all the energy of the electrons will be lost in inverse Compton scattering, and there will be no more energy left in the electrons to produce more synchrotron radiation. The implication of this is the following. If you look at compact radio sources, which are seen by intercontinental, very long baseline radio interferometers, you detect synchrotron radiation from quasars, blobs emitted by quasars, and so on. These have very high brightness temperature. Brightness temperature is a measure of the intensity of radiation. It is the temperature of a hypothetical body which will emit the same amount of energy at that particular frequency. Now, what radio astronomers have found is that when you look at extremely compact synchrotron sources with intercontinental baseline interferometry with an angular resolution of milli-arc second, there seems to be a limit to their brightness temperature. And the limit to the brightness temperature is around 10 to the power 12 Kelvin. It's almost as though, like in Chandrasekhar mass limit of white dwarfs, when the bucket fills and the mass reaches 1.4 solar mass, the bottom drops out and there is a collapse. Similarly, if the brightness temperature of the synchrotron source reaches 10 to the power 12 Kelvin, then the inverse Compton scattering reaches a catastrophic efficiency, and the brightness of the synchrotron source never increases beyond about 10 to the power 12 Kelvin. And now this active galactic nuclei seen in gamma rays by the Fermi Large Area Telescope, one believes that the only plausible mechanism is inverse Compton scattering of synchrotron photons of relativistic electrons. Finally, to conclude, let us go back to this giant gamma ray bubble near the center of our galaxy. As I said, there are electrons and magnetic field. The electrons gyrating in the magnetic field produce synchrotron radiation. The electrons scattering off the synchrotron photon produce ultra-high energy Compton scattered photons, synchro-Compton radiation. Now here is our galaxy in the microwave spectrum at 23 gigahertz, taken with a satellite known as WMAP. We will discuss this at length when we discuss cosmology. Now all I want you to see is that looking straight near the center of the galaxy, you see something like the bubble. This is synchrotron radiation produced by electrons emitted from the vicinity of the central black hole at the center of our galaxy. So the relativistic electrons scatter off synchrotron photons and produce inverse Compton scattered bubble, which is what you see in gamma rays at very high energy. So with that, we conclude this discussion of Compton scattering and its importance in high energy astrophysics. Do go and revise some of the formulae from our earlier lecture on radiation from relativistic charges and try to listen to this lecture more than once. In the next lecture, we will switch gears once again. We shall discuss celestial masers. You all know what masers and lasers are. We will discuss masers in interstellar space of our galaxy and in external galaxies. Till then, thank you very much.